Welcome to Applied Statistics, Module 8. This is Brian Powers, and we're going to be looking at the last couple of things, goodness of fit tests and ANOVA tests, comparing more than two means. But first, let's talk about goodness of fit. The idea is this. You've collected some data that is supposedly from a given probability distribution, and one simple example would be that you've got you rolled a die a number of times and somebody told you that it's a fair die, but you aren't so sure. So you collect the data, how many ones, how many twos, how many threes you got, and you look at that and say, oh, I didn't get a lot of fives and sixes and I got a lot of threes and fours. I wonder if this is a weighted die. Well, the question is really asking, can we attribute this difference from what you expect to chance, or is it so different that it's more likely that it's an unfair die? That's what a goodness of fit test is designed to do. And so what you do is you're comparing each of the outcomes that was possible, how many times you observed it with how many times you expected it, or what proportion of times you expected it. And there's a formula that turns all these numbers together and gives you a statistic called a chi-square statistic. Anyway, this statistic, it has a known probability distribution, and you can calculate a p-value and do a hypothesis test. So that's the idea of a goodness of fit. You're seeing how well some data fits some model or some probability distribution. And I'm not going through the formula for the statistic because it's easily calculated by software. And so the chi-square distribution looks a little bit like this. It's a distribution which takes one parameter called the degrees of freedom. The degrees of freedom of the chi-square distribution happens to also be the mean of the distribution. And for our purposes, for the chi-square distribution for goodness of fit test, we're going to have the degree of freedom is one less than the number of possible outcomes. So for rolling a six-sided die, the degrees of freedom would be 5. Anyway, you calculate the p-value is going to be the probability that lives in the tail beyond the chi-square statistic that we calculated. That's the p-value. And so if the p-value is small enough, we would reject the null hypothesis, right? So anyway, this is the setup for the hypothesis test. We're asking, does some collected data come from a given distribution? And the null and the alternative hypothesis are always going to look like this. The null hypothesis says yes, and the alternative says no. Now, there's different ways that you could phrase the null hypothesis. The null hypothesis could be phrased all of the probabilities equal 1/6 for rolling a six-sided die, like P1 equals P2 equals P3 equals P4 equals P5 equals P6 equals 1/6. Or you could just say it's a fair die versus it's not a fair die. We calculate a chi-square statistic, and this is, remember, what we do for calculating the statistic, we assume the null hypothesis is true. We say, okay, suppose the null hypothesis is true. How unlikely is the data that we observed? And that is the p-value. And remember, if the p-value is very, very small, smaller than our given significance level that we're using, usually it's 0.05, but it could be different, we reject the null hypothesis. Okay? That's a goodness of fit test. Now, the second topic is called an ANOVA test. Now, this is when we have 3 or more populations and we want to compare them, and we are interested in the population means, the averages of the population, right? We want to know if all of the populations have the same mean, or I should say, if at least one of the populations has a different mean than the others. And so the concept behind an ANOVA test is if we take the population as a whole and calculate the sample variance, compare that to the variances of all of the individual samples. So we can pool all of our data into one big sample and look at that, calculate that variance. Is that different enough from the individual samples variances or not? And that's the question. We calculate a statistic using a table, and I'll get to it in a second, but this is the idea. It is the decrease in variance by splitting it into individual like subgroups based on the populations. Does that decrease the variance significantly enough? That's the idea. All right. So before you do an ANOVA test, these are really the 4 requirements that you need. If you've got K is the number of populations that you're looking at, you want to have a simple random sample from each one of them. Remember, simple random sample means you're just selecting. You're just, it's really a random selection. There's no you're not biased in taking sampling like the ones that are easier to look at or anything. It's just really just a random smattering sample of of each population. The samples don't even have to have the same size. They can be different sized samples as long as they're all random. Also, the K samples need to be mutually independent, which is to say the values you observe in one sample have to have nothing to do with the values you observe in the other samples, so they don't influence each other. That's what independent means. The samples don't influence each other. And we're also assuming that the populations we're sampling from are normally distributed. Now, this assumption is usually, it can be tested for separately. What we can do is, there's something called a normality test we're really glossing over in this course, but basically you can look at your samples one by one and check whether the samples look like they are normally distributed. And you can actually run a little hypothesis test on that separately, which is to say the null hypothesis would say it does follow a normal distribution. The alternative is it doesn't follow a normal distribution. And you see whether the data is close enough to a normal that you won't reject the null. Notice that's essentially a goodness of fit test. We just call it a normality test, and you could run that in StatCrunch and actually do an example of that, I believe, in the next video. Anyway, the other assumption is that each of the populations has the same variance. And you can test that assumption by just comparing each sample's sample variance or the sample standard deviations. If they're close to each other, then you can say, okay, that assumption is probably met. If at least one of the samples has a vastly different standard deviation, then you have to pause and say, you know what, I am not meeting the requirements for an ANOVA test, so I have to stop and say that you can't run an ANOVA test. You can't be satisfied with your conclusion from an ANOVA if these 4 requirements aren't met. So anyway, when you do the test, you'll calculate a statistic we call an F statistic because it follows what we call an F distribution. Okay, I'll just show you what an F distribution looks like. It actually looks a lot like a chi-square distribution in a way. It's a distribution where it takes positive values, and it has 2 parameters, a numerator and denominator degrees of freedom. So in this chart, you can see there's 4 curves for 4 different F distributions. The first is 3 and a 3 for the numerator degree of freedom and 5 for the denominator degree of freedom. And then there's 90 and 10, 10 and 90, 50 and 50. Anyway, don't worry too much about this. You'll be using software to calculate the F distribution probabilities, and you can play with the F distribution calculator in StatCrunch or any number of applications online. There's so many of them online nowadays. Okay, so here's maybe the scariest part, but I'm going to walk you through it. When you are doing an ANOVA test, you set it up like this. The null hypothesis is that, so remember you have K samples from K populations. So the null hypothesis is that all of the means are equal to each other. mu1 equals mu2 equals mu3 equals mu4 all the way up to mu k. All right? And the alternative isn't that all of them are different, it's just at least one of them is different. You could have all of them the same except for one. That would violate the null, and you would go with the alternative. So the alternative is at least one of the means from one of these populations is different than the others. Okay, now I'm going to show you an ANOVA table, and this is just a way that the F statistic and the p-value are calculated. Those are at the end of the table, they're the last things that are calculated. So we start out with what are called the sum of squares between the groups, within the groups, and then the total sum of squares. So this is the sum of the squares of the differences from the mean. So take, for example, each group, right? When you calculate the variance of a group, that's actually the sum of squares from each observation from the sample mean, and then the variance is divided by the one less than the sample size. Well, it's based on this SSE. Anyway, you just add up all of those from each of those groups. You can actually back out of the variance from each group and to get the sum of squares of the errors. And then this total sum of squares is based off of the variance of the whole group. It's the how much you pool all of your data together, and you calculate the sample mean for your combined data, and for each data value, how much does it differ from that sample mean? Square it. That's a squared difference. You add up all of the square differences. That's the sum of square total. So actually, from the sum of square total, you can back out to get the sum of square between groups. Those are the first values in the first column, the sums of squares. And the next is the degrees of freedom, which just follows this formula. N is the total sample size. This is all the total sample from all of the groups added all together. And then you have K is how many groups or how many samples you've got. So anyway, the mean square for each of these is, you just take the sum of squares between groups divided by the degrees of freedom for between groups, and you get what's called a mean square for between groups. It's kind of like variance. And then you do the same thing within groups, and those mean squares, the ratio of them is your F statistic. And your F statistic is going to have two degrees of freedom, remember, a numerator degree of freedom and a denominator degree of freedom. Those are coming straight from the table. The numerator degree of freedom is going to be this k minus 1. The denominator degree of freedom is going to be n minus k. So usually the numerator degree of freedom is going to be a lot smaller than the denominator degree of freedom. Anyway, you get an F statistic. Your p-value is going to be the probability in the tail beyond this F statistic, and that's going to be calculated for you. So you can calculate that using software. And I do an example of this in detail in the next video, but this is an ANOVA table. And the thing to remember is really all of these numbers really cascade from left to right. And you can see just here with arrows how each of those kind of goes together to get you your next value. Anyway, your conclusion of the hypothesis test is just like any other. You look at the p-value. If the p-value is small enough, you reject the null hypothesis. And you're really comparing it to your stated alpha level, your significance level. If it's small, that means the null hypothesis is not very plausible given the data, so you reject it. And that's it. So, okay, watch my next video, which is going to go through some examples, and you'll really get a sense of how you can use software to help you do all of this. And I don't want you to be afraid of ANOVA tables. They're very orderly, and once you've looked at them a couple times, you'll see how there's this pattern in them. Okay, that's all for now. Good luck with your work.